Let me begin by thanking the organizers for putting together such a stimulating conference and for inviting me to speak. So I'm going to talk about unitary semiclassical black hole evaporation. For the experts in the room, this might sound like an oxymoron, but I'm going to present a picture of unitary black hole evaporation that is truly semiclassical throughout. Okay, the essence of the information paradox can be captured by studying the entropy of various subsystems of an evaporating black hole setup. The first quantity is the fine-grained entropy of the Hawking radiation, which, as Hawking found, simply increases as a function of time and saturates at some large but finite value. The second is the coarse-grained entropy of the black hole, which is the Bekenstein-Hawking entropy, which is understood as a measure of the dimensionality of the black hole Hilbert space, and it's given by the area in Planck units, and it simply decreases as a function of time and vanishes at late times. It is the fact that the red curve exceeds the blue curve, that it's larger than it, is indicative of information loss. It seems to say that the black hole and the Hawking, the amount of entanglement between the Hawking radiation and the black hole is much larger than what the black hole has room for. Another curve which is often drawn is the Page curve. It is what we expect of unitary black hole evaporation. What it says is that for the first half of the black hole lifetime, the black hole builds up entanglement with the Hawking radiation almost as fast as it possibly can, given the temperature. And once it gets maximally entangled with the radiation, this time is called the Page time. Any subsequent Hawking mode that is emitted must necessarily reduce the entropy until the entropy goes down to 0. Reproducing the Page curve for the black hole and the Hawking radiation is tantamount to resolving the information paradox. So the plan for this talk is to study this in the context of JT gravity coupled to an external system that absorbs the Hawking radiation, and the plan is to track the evolution of the von Neumann entropies of the, sorry, I forgot to say that I'm going to consider an eternal black hole in JT gravity and evaporate one side of that eternal black hole into an external system. And I'm going to track the evolution of the von Neumann entropy of that evaporating side, along with the entropy of the extracted Hawking radiation. The tool I'm going to use to compute the entropy will be given by this updated version of the RT formula of Engelhardt and Wall, which is to evaluate the generalized entropy on the quantum extremal surface, namely the surface which extremizes the generalized entropy. And the goal is to reproduce the Page curve for R, the right side, and the Hawking radiation. I'm going to consider, again, the simplest possible setup, which is going to be JT gravity coupled to conformal matter, governed by the following action. We know that this theory localizes on ADS2, and the gravitational dynamics are given entirely in terms of the reparameterization T of U, where U is the physical boundary time, and T is the Poincare time. The matter sector is going to be given by a boundary conformal field theory, where the boundary is at z equals 0, on the background metric being Poincare ADS2. The eternal black hole solution that we're going to consider is a vacuum solution of the JT equations. Namely, what that means is that the bulk quantum fields are in the Poincare vacuum. So this is what it looks like. The reparameterization is just this simple function where T naught is the temperature of this black hole. And so now we're going to include this external system that's going to absorb the Hawking radiation. We take that to be a bath, BCFT in the vacuum, defined on this flat metric, where the physical time in this system is to be identified with the physical time on the ADS2 boundary. We couple these two systems at U equals 0, and we model this coupling as a quantum quench of two BCFTs, removing the boundary between them. The spacetime that you get after you glue these two systems together looks something like this. So the bath CFT is glued to the ADS2 bulk along the physical boundary, identifying the two times. And and after you do this, you would need to back-react. You would need to solve again for the reparameterization in the ADS2 spacetime, and that's given here in terms of some implicit function f. This reparameterization gives you a relation between, for example, the null coordinates on the ADS2 side and the null coordinates on the bath side, given by the same reparameterization. Now, to solve for this entire spacetime, we need to know what the stress tensor profile is. In the past, over here, the right movers continue to be in the Poincare vacuum, but the left movers get affected by the bath. What happens is that the left-moving vacuum for the bath now sort of goes through the boundary into the ADS2 side, and to know how that is measured on the ADS2 side, we need to take into account, or we can compute that using the Weil anomaly from the transformation of going from the vanishing stress tensor in this metric to this metric. Another thing that happens when you couple these two systems is that you inject some energy into the two systems coming just from the quench protocol, and we model that as a delta function stress tensor with amplitude ES being the energy of the shock. That's what I'm going to call it. Okay, we have the stress tensor profile everywhere, and we work in the semi-classical limit. We source the JT equations with the expectation value of the stress tensor to determine the dilaton phi and the reparameterization. So now we have the space-time everywhere. Next, we need to compute the bulk entanglement entropy, and we are interested in two kinds of entropies or bulk entropies in the spacetime. The first is an entropy of an interval which is anchored on the ADS2 boundary and which extends into the ADS2 bulk. This will be relevant when computing the generalized entropy. This computes this piece. The other piece that we're interested in is a half-space interval which computes the entropy of the bath or computes the entropy of the Hawking radiation, because the Hawking radiation is going to flow into the bath. The way that we compute this entropy is by following these three steps. The first is to transform to a coordinate system where the stress tensor is trivial. We compute the entropy in that coordinate system. Then we transform back to physical coordinates and cutoffs. Okay, so now we have all the ingredients we want to find the generalized, to find the quantum extremal surfaces and evaluate the generalized entropy. So we extremize it in this fashion, and so we essentially have to move this surface chi around until we find the quantum extremal surfaces. There will be two interesting branches. The first is to look for a quantum extremal surface near the bifurcated horizon. I'm going to call this the early time branch. The bifurcated horizon continues to be so even after turning on the coupling, continues to be a classical extremal surface, but it is not quantum anymore. The reason being is that the state on this slice after the coupling has been deformed because some of the Hawking radiation escapes the ADS2 space and enters the bath. And therefore, performing a variation of, for example, the dilaton piece near the bifurcated horizon, one would obtain, it would go as L squared over G Newton, where L is the variation parameter, while the variation of S bulk will be linear in L multiplied by C. C is the central charge of the bulk BCFD. This implies that there's a quantum extremal surface at a distance that goes as C times G Newton away from the event horizon, or the bifurcation surface. This actually should be a minus CL, but it doesn't matter. So you do this, and you find that there's a locus of quantum extremal surfaces near the bifurcated horizon. They look something like this. Each point corresponds to a different boundary point in this fashion. And you find that there's an accumulation point somewhere here. OK, so that's the early time branch. There is another, there's another set of relevant quantum extremal surfaces, all of which are to the future of the shock, which I call the late time branch. And let's go through the extremization procedure a bit more carefully. So we first try to extremize along the outgoing direction. And given that this is a black hole spacetime with an event horizon, we can search for a surface near the apparent horizon. So that's the region where the outgoing derivative of phi is 0. OK, but that's not enough to specify the surface. We also need to extremize along the ingoing direction. Now we have a bit of an issue. The ingoing derivative of phi near the apparent horizon is actually order 1 and negative. This is just a statement that the area of the transverse spheres in a black hole spacetime near the apparent horizon, at least in this case, are contracting in the ingoing direction. And therefore, this term here is going to be 1 over g Newton, and so must be compensated by a large gradient in the bulk von Neumann entropy. Now, we can actually achieve this, and schematically, this is not exactly what the equations are, but schematically, this is what happens. The entropy in the bulk is roughly, it goes as the central charge times a log of the length of the interval. And therefore, if we work in the null limit, taking into account that the derivative or the gradient is c over the length, which take derivative of this guy, this means that we can balance this equation by taking the length of the interval to be c times g Newton. Now you might worry and say, but isn't this interval really, really small? No, it's fine. And the reason being is that we can work in the limit where the bulk central charge is large, but not too large, so that the length of this interval is parametrically larger than the Planck length. OK, so we have two sets of quantum extremal surfaces, these green guys and these purple surfaces near the apparent horizon. And I'm going to plot what they look like as a function of time. Before I do that, on this plot, I have the Bekenstein-Hawking entropy of the right side of this spacetime, and where I've isolated the ground state entropy from the thermal entropy above extremality. When I write delta S, I will always mean the thermal entropy above extremality. And what happens is that it gets a spike because of this shock that falls in, and then it decays exponentially. That's just a feature of JT gravity. OK, so let's look at the early time branch. So what does this look like? So the quantum extremal surface, as we said, is near the bifurcated horizon. This means that the dilaton term is going to stay essentially constant, and all of the time dependence is going to come from the bulk entropy piece, where at late times you find that this term simply increases and saturates at some value. But something interesting is happening at early times. So when you first turn on the coupling, what you find is that the entropy first goes down. This is simply because the Hawking radiation is escaping the system. That Hawking radiation was entangled with the left CFD, or left boundary. But then, after the scrambling time defined with respect to this energy that falls in, the entropy turns around. I should say that this scrambling time for near extremal black holes was found by Leichenauer a long time ago, and we seem to reproduce it here. But let me explain why this effect happens. So when you throw energy into a black hole, you in some sense, rejuvenate it. Let me take a step back. If you have a black hole that is maximally entangled, and then you throw some pure matter into it, you rejuvenate the black hole, allowing it to get more entangled with its Hawking radiation. But in order for that to happen, you need to wait for a scrambling time for the black hole to actually have access to these new space of states. Okay, so that's the early time branch. Then there's the late time branch, which, as we said, the quantum extremal surfaces are near the apparent horizon. This means that the dilaton value in this branch of the entropy will simply follow the Bekenstein-Hawking entropy all the way. So we have these two contributions, these two possible branches for the entropy, and the actual von Neumann entropy of R is the minimal one. So we need to apply the minimality constraint, and lo and behold, we have a page curve. The entropy of R goes up, and then it turns around and comes back down. Okay, so does this solve the information paradox? No, not yet, because we didn't analyze the bath. So the question is, what does the entropy of the bath do? So you can compute this using CFT techniques, and you find that the entropy simply goes up and saturates at this value. We don't really understand this factor of 2 yet, but it's 2 times the thermal entropy of the initial energy of the black hole plus the shock. And you can, so in order to deduce if there's information loss or not, you need to check if this entropy violates any entropic inequality. One such inequality is the Iraq-Kilib, which places an upper bound on the entropy of the bath being less than the entropy of the sum of the entropies of the left and the right. Plotting SL plus SR here, that looks something like this. And so we see there's not a problem when the ground state entropy S0 is large. But just because this is not a problem does not mean that there is not a problem in general. In particular, something that we can do in this case is that we can ramp up the energy of the shock, which was thrown in, and all our calculations actually just simply go through. And you find that the entropy of the bath increases monotonically and exceeds the entropy of the left plus the right. So this is information loss. So we failed to find a page curve for the bath. And this reproduces the standard Hawking result. This is actually a sanity check. The calculation that we did is identical to Hawking's calculation, so it's no wonder we got the same result. And so this doesn't resolve the information paradox. But now let me tell you how to resolve it. Consider the following crazy proposal. Let's say that the bulk bath CFTs living in this 1+1 dimensional spacetime is holographic. So this 1+1 dimensional spacetime or system is dual to a 2+1 dimensional bulk coming out of the board. This slice here, it corresponds to this slice of the spacetime, where the new holographic direction is pointing downwards. Let me see. Now, here on this spacetime, we have a BCFT on a strip. On this spacetime, we have a BCFT on the half-line. It is a prescription of holography for boundary conformal field theory to extend the boundary of the conformal field theory into the bulk as some sort of end-of-the-world brane, or what we call an IR brane. Okay, so this is what you'll find. And at this stage, we need to be careful about what we mean by the boundary holographic system. It's not actually this. Remember, the JT theory here and whatever lives in it is supposed to be dual to the 2 quantum mechanical systems on the left and the right. Therefore, the boundary holographic system is composed of these 3 systems, and the JT theory should be thought of as living in the bulk on what we call a JT brane. This JT brane lives on an ADS2 slice of the ADS3 which is in the holographic direction. Okay, now let me tell you about the dynamics of this three-dimensional bulk as we couple B to R. So what happens is that the IR branes connect, and as you evolve forwards in time, the IR brane simply recedes into the bulk in this fashion. Okay, now let's compute the entropies. So say we want to compute the entropy of the left. We can use the usual RT formula, or HRT, in the 2 plus 1 dimensional bulk. And it says that the entropy of L, for example, is simply given by the area of this RT surface, or rather there are two contributions coming from that surface. One comes from the contribution at this anchoring point on the JT brane. Because the JT brane is dynamical, you actually pick up a dilaton factor. And you also get just the length of this RT surface, which gives you S bulk. So the bulk entropy on this slice has been geometrized into the area of the RT surface in 3 dimensions. This is what usually happens. So this is at this time. Let's evolve to a time after the shock. Now the bath has non-zero entropy, and it now has an RT surface in the bulk. And that looks something like this. It's this orange line. The R system gets a new contribution to the RT surface, which is given by this green line. And it is this contribution to the to the entropies of R and B that is responsible for the for the increase of the entropy at early times of the two systems. Evolving slightly further until we reach the page time for the right, you find that so you develop a new RT surface for R, which starts at this point and ends on the JT brane. This computes this late time branch that I talked about earlier. And at this time, we have this interesting situation where we have an entanglement shadow in the 2 plus 1 dimensional bulk. There's a region of space that is not contained in the entanglement wedge of any single boundary system. I should now also say that because the entropy of the bath given by this orange RT surface just increases a bit more at this time. Now we evolve even further. What happens now is that, or something that you should have noted in the previous slide, was that there was another candidate RT surface for the bath, which was given by the union of the RT surfaces of the right and left, which at this point in time actually has smaller area than the orange line, than the orange RT surface. So the von Neumann entropy of the bath is now computed by the dark blue segment, and this continues to be true for all time. And so we see that this 2 plus 1 dimensional bulk helps us enforce the Araki-Lieb inequality, the fact that B is bounded by SL plus SR. This result that I reviewed, this wrong result, which violated Araki-Lieb, is what comes from focusing only on this branch of the RT, or this RT surface. The fact that it becomes non-minimal. This is really, really crazy. This is saying that the entanglement wedge of the bath reaches all the way and includes this light blue region of the JT brane. This light blue region in this 1 plus 1 dimensional space corresponds to a region that contains the black hole interior. This says that the black hole interior is dual to the bath. This realizes ER equals EPR. Now, unfortunately, this doesn't realize the octopus spacetime, but as Stephen Schenker said, now we have a nice single fillet of salmon. Okay, so the punchline is we managed to obtain a page curve for both the evaporating black hole and for the radiation. And in some sense, we also found, or we in some sense pinned down, quote unquote, Hawking's mistake, which is that he didn't know about the minimality condition of the RT formula, but also he didn't know about the RT formula. Also, just before I go into question and answer period, somebody should ask me about pure states. Thank you.
Questions for Ahmed?
So, in my review talk, I promised everybody that the quantum extremal surface would lie behind the event horizon, and as seen in pretty much any one of your other slides, here it does not. So I was thinking throughout your talk, why does this happen? And I think it has to do with this shock where you couple the boundary to this other system and it emits a pulse of negative energy. I'm pretty sure that that pulse of negative energy will cause the generalized second law to no longer be true on the causal horizon. That's the uppermost, that thing there.
That's not the horizon. The horizon is here. That's just the extension of the past horizon from the left.
Well, so the one on the left is the boundary of what an observer can see who stays in the original space-time, maybe? Oh, I'm not saying you necessarily have a contradiction here. That's certainly, the fact that that dashed line that does not satisfy the generalized second law is why you violated that theorem. But do you have a comment on what you think the moral of that is?
I'm not sure I understood, but let me correct something. I think you said that this yellow line has negative energy. Did you say that?
I thought you said that.
No, it has positive energy.
It has positive energy.
Yes, yes. But there's negative energy that falls in because, sorry, there's the fact that you have the vacuum in the bath, that translates in the bulk to having negative energy falling in. And the interpretation of that is simply that the black hole is evaporating. That the Hawking radiation coming out of the past singularity is not being reflected off the boundary and falling in, but rather just going into the bath. That absence of the positive energy is that negative energy.
There are situations where you can violate the generalized second law because you take your slice you're evaluating S out on to only go a finite distance instead of all the way to the edge. It's probably related to that.
Okay.
Sandeep?
I'm very confused by your talk, so maybe my question is off base, but you know, the model at root is not so different from the models looked at 30 years ago by CGHS and their variants, where a very careful calculation was done of the entanglement in the radiation outside when, say, you threw in a pure state or something, and one found that you could have an arbitrary increase in the information loss. What's different in this model that's allowing you to avoid that conclusion?
You didn't use the RT formula. So here the trick that we're using. So let me go back first. So this represents what you guys found. The entropy of the Hawking radiation, or the bath in my case, simply increases and you have information loss. Yeah, the kind of calculation we did here is identical to the kind of calculation that you did. But now I'm proposing a different calculation, which is using this 2+1 dimensional bulk. The formula that we use to compute the entropy of the bath is not the standard CFT formula. We're using the RT formula in the 2+1 dimensional bulk.
But, okay, then we should continue, but you are taking the same 1 plus 1D theory,
Yes,
right?
yes.
So, I mean, you mean to say the RT formula doesn't agree with Cardy's formula in a 1 plus 1D CFT? Or because that's what one used in the original calculation, although it wasn't
Yeah,
Cardy's formula.
what this is saying is that when you have, when gravity's in the game, you need a new set of rules. And the new rule here is that you need to use the RT formula. That's what I would say.
Yeah, just to make sure, this 1 plus 1D theory is not semiclassical.
Maybe that's an interpretation.
I think that's the reason, right? I mean, 2 plus 1 is a semiclassical, but it's just deviated. That's why it's not information loss.
So in the
Where am I looking?
in the later part of your talk, so are you putting the dual of JT gravity on the boundary of holographic to the BCFT?
Sorry, the dual of JT, can you say that again?
So what is I wonder what is the boundary configuration?
The boundary configuration.
Yeah. So where is the dual of JT gravity?
It's these blue dots.
So is this the boundary of 2D holographic boundary CFT?
Yes, it is where the boundary of there's a 2D CFT living here, and we have these two quantum mechanical systems which live on the boundaries of the 2D CFT. Yes.
I see.
Ahmed, if I make sure I understood something correctly. So the key thing that you really want is factorization across quantum quantum entanglement wedges. That you have two quantum entanglement wedges, they have the same information for complementary regions. So there's no such thing as an entanglement shadow, a phrase that I.
Well, sorry. Entanglement shadow just.
I mean.
I just meant in the sense that it cannot be reconstructed from any single region individually. Maybe is that? I mean, that was the definition I gave for shadow, but maybe there's a.
No. I mean, in classical description of entanglement wedges, in the semi-classical description, there is no such thing as an entanglement shadow because once you're given a pure state of a combined system, if you have a HRT surface, then the entanglement wedges of the region and the complement, that gives a complete factorization of the full spacetime. There's no part that's missing, except in the future and past of the HRT surface.
Yes. I think you're just saying that if I have the entire system, then I know what's inside this entanglement shadow.
Right.
Yeah, no, I completely agree, of course. Yeah.
So let's take one more question from Dan.
Well, so I already asked you about pure states before, so I'm going to ask you about something different. So this bulk theory of Jakiv-Teitelbaum coupled to a holographic CFT, is this supposed to be a UV complete description all by itself? If the answer is yes, then I don't see why we should think of it as being holographic and dual to these two separate boundaries. We should just be able to compute everything directly in this bulk description, and then I think as Sandeep was saying, it seems like there should be information loss. So I think probably for this calculation to be justified, it somehow must be the case that this bulk description isn't really the right thing, right? Like the right thing is this holographic, something like SYK with a fixed instance or something, where we view the JT coupled to matter as only an effective description that has to be UV completed into the CFT. So do you agree with that, or what do you say about that?
I would say that within the UV complete theory of JT plus CFT, perhaps there's a new set of rules that we just have not uncovered yet that will give us the right answer.
But I mean, then it's just information loss, right? It's
just
bulk effective field theory. So I mean, it must.
No, it's information loss if you use the standard, if you.
But I mean, to be clear, like for example, if you just forget about the matter, just do Jakiv-Teitelbaum, right? So then that theory, can be exactly solved either in the way that Jeffress and I did, or in the way that Steve Schenker talked about in his talk. In either way, it doesn't have a holographic dual, right? It's
Yeah,
not
yeah.
dual to two quantum mechanics living on those endpoints. So when you assume that, you're somehow assuming that the bulk description is not really the right one.
Well, I mean, ultimately, we consider this model not because it's UV complete or anything like that. It's just that we can do the calculations.
Yeah.
So,
Right.
I don't, in a sense, I'm continuing the previous question because JT theory has a limited range of validity. When you ran, you showed nicely that you satisfied the Iraqi-Lee bound if you were not too far from extremality, but then you ran into trouble if you were farther. I was expecting you to say at that point that there's a limitation on the validity of the JT theory, and it's only good if the non-extremal entropy is sufficiently small compared to the extremal entropy. I don't have a technical reason for that, but I expected that to be the situation.
no, thank you for that comment. So this is not necessary. So you can run into a problem not by just increasing ES to be very, very large, but you can continuously feed the black hole with small bits of energy. So you throw some ES, which is small, you allow the black hole to evaporate, then you throw another shock, and you wait, and so on and so forth, and you would end up with the same conclusion. All the meanwhile, you're within the approximation where the near extremal entropy is small. The thermal entropy is small.
Okay, before we thank Ahmed again, I'd like to just ask you to remain seated for a short announcement. So let's thank Ahmed.